This video is meant as an introduction to the use of Kp and calculating Kp and also calculating partial pressures. You should already know how to write expressions for Kc, equilibrium constant, using concentrations, and how to calculate Kc from concentrations, and also if you're given changes to the number of moles. So there are some useful similarities between Kc and Kp that we should be aware of. You should already know that if you were writing an equation for Kc from this equation here, for this example, we would be putting the right hand side, the products, on the top of the equation. We would be using square brackets to show concentration, and where there are numbers in front representing the number of moles in the balanced equation, we would take them into account by, for example, raising the power of concentration of D to the power 3. And we would then put our products on the bottom, so I would have A concentration of B squared. That's how I would do it for Kc. Kp is going to be an extremely similar format, so it's still going to be right hand side over left hand side. I'm still going to have the numbers in front raising to powers of the concentration, but in this case I'm not doing concentration, I'm going to be doing pressure. So the P in Kp stands for partial pressure, which we'll explain in a minute. So there are various different ways of doing this. Generally I like to use a lowercase p, which is slightly italicized, and I'm definitely going to use curly brackets, not square brackets. Sometimes you will see the brackets not there, and that's fine as well. Sometimes you'll see a bigger P, so sometimes people will use a capital P. It's rather frustrating actually, there doesn't seem to be a completely used format that's used all the time for everybody. So the reason I like to use a lowercase p is in the case of, for example, if you had an equilibrium involving phosphorus pentachloride, you're going to end up with sort of this situation. That is definitely the case where you want to use the brackets, otherwise you're going to have far too many p's going on in your equation. So Kc and Kp similarities, they are done in the same mathematical format. Other similarities, I would work out the units using the same idea of working out what's on top and what's on the bottom, and we'll do some units in the examples. So what's different about Kc and Kp? Well, clearly the units are different, and clearly the places that we can apply them in chemistry are going to be different as well. So if we looked at these two examples where we had two different equations where the reactants and products were in different states, then I could use Kc for both of these examples. And the reason I could use Kc for both is because obviously solutions can be measured in moles per dm cubed, so I can work out a concentration. So the bottom one is obvious, everything is aqueous, but also I could work out the concentration of a gas. If I know the volume of my container and I know how many moles of gas are in that container, then of course I can work out moles per decimeter cubed. I cannot work out concentration for solids, and I cannot work out pressure for solids, so they never appear in a Kc or a Kp equation. So differences in the units, therefore, if I was working out the units of Kc for the top expression, so be really careful, because sometimes of course you get gases and then you're asked for Kc, so just make sure that if you were doing that you were actually using concentration units and not trying to work out partial pressure. So if I was working out Kc and I was trying to work out what the units were in this, I would have moles per dm cubed for my concentration of C, moles per dm cubed for my concentration of A, and moles per dm cubed for B. I can then cancel out anything that's on both sides, and my final unit would be mole to the -1 dm cubed. So The difference with Kp is there are two possible ways of doing the units. So it would be the same format. My options would be that pressure could be measured in atmospheres, in which case my units would be atmospheres to the -1. Alternatively, they could be in kilopascals, in which case my final unit would simply be in kilopascals to the -1 for this example. So actually the units are slightly easier because I haven't got those grouped together units of moles per decimetre cubed. I've only got to worry about one unit, whether it's to the power 1, 2, -1, -2, etc. So we've been talking about this P, and I've occasionally been calling it pressure, but it actually stands for partial pressure. So what is partial pressure, and what do we mean by that? Well, imagine I have a container, and in my container there is 1 atmosphere of pressure, which is about 100 kilopascals. So some exam boards will use both units for pressure, some exam boards will concentrate on atmospheres, and some will concentrate on kilopascals. The method for solving the problems does not change with the units, but the final answer would be different. So imagine I have a container, and this particular container only at the moment contains one particular gas, which is represented by the blue circles. So at the moment, the entire pressure of this container, the whole 100 kilopascals, is made up by this blue gas. So this blue gas is contributing to 1 atmosphere of pressure. This could be something that happens, for example, at the start of an equilibrium reaction, or when I'm setting it up, and I've only got reactants, and I haven't actually reached equilibrium. So let's imagine that we leave these blue particles of gas, and it turns out that they can react and turn into red particles of gas. So now we've reached a position where it's at equilibrium, and it turns out that now there are 4 particles of blue gas and 3 particles of red gas. So we can say that the partial pressure, assuming the pressure has remained constant, which it normally would in a sealed container at fixed temperature, the partial pressure of the blue gas is going to be 4/7 of the total pressure, because 4 of the particles are blue gas and 3 of them are red. Similarly, the partial pressure of the red gas is going to be 3/7 of my original at 1 atmosphere, or 3/7 of 100 kilopascals. And that's because, remember, no matter what the gas is, it's the number of moles of gas in a particular volume at a particular temperature that will determine the pressure. And so therefore, our PV equals nRT tells us that it's simply a case of how many moles of gas there are will tell you how much pressure it is contributing to the mixture. So we have 2 little definitions that we can get out of that. We've got this thing called mole fraction. So the mole fraction we just saw was either 3/7 or 4/7. That's obviously a very simplified example, and I was counting individual particles. We're going to count moles like we normally would. So the mole fraction of a gas is simply the moles of the gas, whatever it is, nitrogen, hydrogen, divided by the total number of moles in the container of gas, obviously. So in that case it would have been 3/7 or 4/7. So it's literally a fraction. Therefore the partial pressure is just how much pressure that one gas contributes to the whole mixture. And so it's going to be the mole fraction, for example 3/7, 4/7, multiplied by the total pressure. In that case it would have been 1 atmosphere or 100 kilopascals. Let's have a look at how we can put that into a calculation. So here's an example. Dinitrogen tetroxide can decompose to form 2 moles of nitrogen dioxide. Very common equilibrium equation. So The question says at 350 Kelvin, this reaction was allowed to reach equilibrium in a sealed container. That bit of information is alright, but we don't really need it. Always we're going to be calculating Kp at a given temperature, so we don't need to use the temperature in the calculation. If it's not in a sealed container, it's not going to reach equilibrium. So the equilibrium pressure was 123 kilopascals. I'm going to need to use that. And the reaction mixture contained 0.32 moles of N2O4 and 1.28 moles of NO2. Calculate Kp. So to do this, we need to work through mole fractions in order to work out partial pressure, because partial pressure is the P in Kp, and that's what goes into my final equation. So, mole fractions. First of all, I need to know a mole fraction was number of moles of the gas divided by the total number of moles. So I need to work out total number of moles of the gas, and that would be 0.32 plus 1.28, which is 1.6. So therefore, my mole fractions, if I write this underneath the gases to make it clearer, notice I'm not bothering about the 2 in front at the moment, so I'm not using the balancing numbers yet. I will need them when I calculate Kp. So my mole fraction is going to be, for the case of N2O4, 0.32 divided by 1.6, and for NO2 is going to be 1.28 divided by 1.6. Now you can leave your numbers like that and multiply them by partial pressure, or you can work them out. So it turns out that this equals 0.2 and this equals 0.8. I would definitely, if they ended up not being very neat, so sometimes your calculator is going to leave them in a fraction form, if they end up being very messy numbers, I wouldn't bother writing the number down. I would simply take it straight into my next calculation. And my next calculation is going to be working out partial pressures. This is the P in my Kp. So partial pressure for N2O4 is going to be 0.2 times 123. That's my kilopascals, and that gives me 24.6 kilopascals. And then for NO2, partial pressure is going to be 0.8 times 123, and that's going to give me 98.4. Always really useful at this stage when you've just worked out partial pressures. Just take a second to check that your partial pressures add up to the total pressure. Do they add up to 123? Yes. Excellent. We can move on with those numbers. So we've got those numbers, and these are the P's in the Kp equation. So then I'm just going to substitute in. Now, as you're calculating, we have a very sort of left to right kind of habit when we're working with equations. We always consider that the direction that we're going in. It's very likely that we'll be told the number of moles or whatever of the left hand side first. So what you've really got to watch out for here is that you remember that Kp or Kc equations are always in the format of the right hand side reactants over the left hand side. It's worth writing it out to remind you that, and then you can put the correct numbers in. So easy. Other thing that's very easy to do is to forget the squared. So I put those numbers in and I get a final answer for my Kp of 393.6, and I round it up to 394 because everything else was in 2 or 3 significant figures, so I don't need to be any more accurate than that. I'm also going to put my units on, of course. I was given it in kilopascals. I've got 2 lots of kilopascals on the top because my NO2 is squared, 1 on the bottom, so if I was working through units, this is what I would have. Cross the 2 out, and actually my unit is just kilopascals. As simple as that.